Prior to learning the hands-on techniques of ultrasound, an understanding of the basic foundational concepts and principles is important for the operator. Ultrasound imaging is among the safest and most universal diagnostic methods ever invented. It provides much of the information that can be obtained by expensive technologies such as X-ray, computer tomography, or MRI, and is the only method that can produce a real-time or live image that can be interpreted and or transmitted at the same time. Let's listen to the National Institute of Health overview
The heart of most ultrasound systems is a device called a transducer, which uses an array of piezoelectric crystals. A piezoelectric crystal vibrates when an electric signal is applied, producing high-frequency sound pressure waves, which we call ultrasound. More importantly, this type of crystal can also work in reverse. It can produce electrical signals when it detects high-frequency sound pressure waves. When a transducer directs ultrasound waves into the body, they pass right through the skin and into the internal anatomy. As the waves encounter tissues with different characteristics and densities, they produce echoes that reflect back to the piezoelectric crystal. This happens more than 1,000 times a second. Returning echoes are converted to electric signals, which a computer converts into points of brightness on the image, corresponding to the anatomic position and the strength of the reflecting echoes. A medical transducer contains a large array of crystals, which allow it to make a series of image lines that, together, form a complete image frame, called a sonogram. In addition, all the crystals are repeatedly activated many times in such a way that a complete image frame is formed around 20 times per second, so that real-time motion is displayed in the ultrasound image.
This is an overview of ultrasound, and we'll go in more detail as we go along. Remember that in dealing with the topic, some theoretical considerations have been simplified. The aim here is not an in-depth technical expertise or an in-depth knowledge of physics concepts utilized in ultrasound. What we begin with is understanding that most imaging is necessarily an aid to diagnosis. Our main aim is to better understand the digital concepts of ultrasound imaging. Technical aspects, which have been greatly simplified here, only serve to facilitate the understanding of the imaging process. Understanding ultrasound physics is crucial for physicians performing ultrasound examinations, whether in primary care, surgery, or emergency medicine. It ensures accurate interpretation and safe use of this valuable diagnostic tool. The use of ultrasound outside the radiology suite has grown markedly over the past few decades. With increasing portability of ultrasound machines has come more frequent utilization of the technology at the point of care site, or where the patient is located. Point of care is a term to describe bringing the sonographer and equipment to the patient. All medical imaging modalities record the interface of energy with tissue as electrical signals that are digitized, and those digitized signals are converted into data to create images. Here we can see the different type of energies that are used. Ultrasound uses sound waves to create images by measuring tissue reflections. MRI utilizes strong magnetic fields and radio waves to visualize soft tissue. X-ray imaging, X-ray passes through tissues and their absorption reveals structures like bones. With CT, it combines X-ray from different angles to create detailed cross-sectional images. And finally, PET, positron emission tomography, detects gamma rays emitted at radioactive tracers injected into the body. The advantage of ultrasound is that it is not using ionizing radiation, it has good spatial resolution, it's low cost, fast, and safe. The energy in ultrasound travels through matter as a waveform. The energy waves travel by compressing and reflection of matter. Dependent upon the matter, the wave will travel at different velocities and in different directions. The intensity of sound waves diminish as they travel through the body. The ultrasound waves travel through tissue by displacing matter, expanding and compressing adjacent tissue. This generates an ultrasonic wave that is attenuated by the tissues that it encounters. The transducer emits a sound wave and receives the echo from the emission of the interaction of the sound wave with tissue. Let's take a look at the modality ultrasound. First, we see a transducer probe. It sends and receives echoes or sound waves. We also have a central processing unit. It's a computer that does all the calculations and contains the electrical power supply for itself and the transducer probe. Transducer pulse controls change the amplitude, frequency, and duration of the emitted pulses from the transducer probe. In other words, this is our technique basically. The display displays the image from the ultrasound data processed by the CPU. The keyboard inputs data and takes measurements from the display. And the disk storage device stores the acquired images that can also be printed. Let's take a look at the computer portion of the ultrasound modality. We look at the computer for computer processing. It processes electric signals that are sent to the ultrasound scanner by the transducer or probe. The scanner processes the signals using sophisticated algorithms. It converts the pattern of echoes into real-time images or video. Let's take a look at the interactions of ultrasound with tissue. The ultrasound creates an energy in the form of an echo wave, which is transmitted into the patient. The transducer also receives those waves that are reflected back from the patient. So it both transmits and receives the echoes. Let's talk about the continuous sound waves being changed into a format for utilizing in the computer and then changed back to a continuous format, in other words, the motion that we see on the ultrasound monitor. This is done through analog to digital conversion. Analog to digital conversion is done in 3 steps. Notice in the first step we have to capture the original signal. Notice that the signal varies, or the sound waves differs over time. We take samples or measuring the different times and the intensity at each of these times. When we've measured them, what we have to do is assign a number to them. In other words, we digitize them. That is the analog continuous signal now being changed into a discrete number. Here we can see the different intensities at different times are changed to discrete numbers. Once we have these, we need to code them or change them into data. Data coding is assignment of a binary bit sequence to each discrete output from the quantizer. Here you can see that each one of the intensities is given a specific corresponding number. Signal being produced, and we are going to sample the echo data so that we can assign specific numbers that can be converted into shades of gray for visualization. Notice that at each point along the wavelength we are assigning a sample or number that is now corresponding to a shade of gray. This is raw data. The raw data is stored in the computer in different lines in a thing called K-space, which is the storage space. Signals that we measure are digitized before being stored in the raw data space. It's simply just a list of numbers representing the corresponding signal intensities. These are used by the computer algorithms to create image display. There are many signals, and you can see how they're stored. The computer then can go into the storage and select the signals it needs to create the visual display. Ultrasound is an acoustic wavelength that is above the human threshold for hearing. It is a mechanical energy. So let's talk about ultrasound production. The transducer produces ultrasound by transmitting 1% of the time and receiving those transmissions or energies back. The reflected echoes return to the scan head, which then converts the ultrasound wave into an electronic signal. This is where we have our electronic signal that we are going to change from analog to digital. When the ultrasound waves propagate through tissue and encounter interfaces between two types of tissue, some of the sound waves will be reflected. This reflected sound wave is called an echo. The goal of an ultrasound system is to make like tissues look alike and unlike tissues to look different. In other words, if there's different densities and thicknesses, we want to be able to see those. Since the transducer is capable of receiving reflected sound signals, it must be set for a specific range of signals to provide for the study expected and eliminate those signals and ranges that are not useful. This is done by preset parameters for both transducer and capture, both of which are critical. Accomplishing this goal depends upon acoustic impedance, resolving the capability of the system, whether it's axial or lateral resolution, the spatial resolution, the contrast resolution, and the temporal resolution. This is the image itself. Beam formation, the ability to send and receive the ultrasound signal. And processing power, and that's the ability to capture, preserve, and display the information. Look at this graphic and see how it demonstrates how the ultrasound image is constructed. You'll notice that electrical energy is converted to sound waves. So we have the transducer, the sound waves being emitted and collected, and that is done by setting the parameters for the collection of the sound waves. The sound waves are reflected by tissues, each tissue having different density and thickness, creating different sound waves or different intensity of sound waves. The reflected sound waves are converted to electrical signals and then sent back to the transducer for creation of the image at a later time. Ultrasound transducers produce pulses of ultrasound waves. These waves travel within the body and interact with the various tissues. The reflected waves return to the transducer and are processed by the ultrasound machine. An image which represents these reflections or differences in intensity of the waves collected is formed on the monitor. How does ultrasound differentiate the different tissues within the body? This is done through acoustic impedance. When interacting with tissue, either the echo will be reflected or absorbed. The amount of difference between the original echo that reached that tissue and the difference after the interaction is the difference in the intensity of the wavelengths or echoes that we're recording to create the images. Let's take a look at how the images are deciphered. You start from the top of the image, which is where the ultrasound probe was placed, and the image shows what organ or tissue looked like from the side. As one looks further down the screen, they see deeper into the tissues. And obviously, as the travel of the echo goes farther in the body and some of it is absorbed, the echo traveling to tissues below the tissues above is weaker. In the final image, or the image that we're viewing for diagnostic purposes, what we must understand is multiple echogenicity. Here we can see the difference between hyperechoic and hypoechoic. An echo is correlated to the type and density of tissue that it is interacting with. And we can see the terms anechoic, hypoechoic, isoechoic, hyperechoic, and reflective. These are all the densities that you can see on your ultrasound monitor. And above we see a fetus, and in each area we show the difference between anechoic, hypoechoic, and hyperechoic. Notice in the circle that is labeled isoechoic, what we're looking at is two different tissues, but they have the same density and thickness. On the other hand, if we look at an echoic piece of tissue, the surrounding tissue is different from the tissue that we see in the circle. There are a few clinical specific situations in which ultrasound is difficult to use or cannot be used based upon the structures that you're trying to visualize. Structures surrounded by bone, such as the brain and spinal cord, do not give clinically useful images, and the attenuation of the ultrasound signal at the air-tissue interface means that the technique is not suitable for imaging structures in the lung or abdominal organs, which is obscured by gas in the overlying bowel. Let's begin by looking at the representation of the echo. We have the trigger event, and we can see the pulsed wave. Then we can see the echo as it goes through the tissue and changes in intensity. The ultrasound waves, pulses of sound, are sent from the transducer and propagate through different tissues, and then return to the transducer as reflected echoes. The returned echoes are converted back into electrical impulses by the transducer crystals and are further processed to form the ultrasound image presented on the ultrasound monitor. Let's talk about the transducer element. The transducer typically uses the piezoelectric crystals or capacitive transducers to generate or receive ultrasound. Piezoelectric crystals change their size and shape in response to voltage being applied. Next, we'll take a look at the generation of the ultrasound wave itself. The transducer generates sound waves in the ultrasonic range above 18 kilohertz by turning electrical energy into sound. Upon receiving these sound echoes, the transducer turns the sound waves back into electrical energy, which can be measured and displayed. Ultrasound imaging is a medical diagnostic technique that uses high-frequency sound waves to create images of internal organs and tissues in real time. To capture and view ultrasound images in real time, one needs to have a good understanding of the anatomy of the area being examined, as well as the ability and knowledge to choose the correct system settings and components to optimally capture the area of interest and have the ability to adjust the modality in real time to successfully capture the images. Attenuation is the pulsed energy from the transducer, the echo being pulsed into the body. As the echo is pulsed into the body, it is stronger nearing the skin level, and as it goes deeper, it's being partially absorbed, and so the echo becomes weaker. At the end of the pulse, we will get reflections. In other words, the transducer will now receive the echoes being reflected by the tissue. Remember, you have like 1% pulse, 99% receiving. There are different ways that the echoes can actually go through the body. They can be scattered, or as they're going through, we have the process of refraction and also diffraction. Sound cannot travel through a vacuum. Sound is a mechanical and longitudinal wave that travels a distance through some sort of media, meaning like the ultrasound wave travels through the tissue. The reason we call it ultrasound is the reflected echoes are higher than those that can be heard by the human ear, which is about 20 megahertz. Let's review the interactions of ultrasound with tissue. Acoustic impedance is dependent on the density of the material in which sound is propagated. The greater the density, the denser the material, the greater the impedance. When we get reflections, which is the echo coming back to the transducer, we know that there's more signal recorded closer to the skin level than there is deep in the abdomen. Ultrasound is a mechanical longitudinal wave with a frequency exceeding the upper limit of hearing, which is 20,000 hertz or 20 kilohertz hearing. Medical ultrasound is 2 megahertz to 16 megahertz, and the ultrasound frequencies in diagnostic radiology range from 2 megahertz to 15 megahertz. 3.5 megahertz is used for general abdomen and obstetric and gynecological imaging. 5 megahertz is vascular, breast, and pelvic imaging. A 7.5 megahertz is typically used for breast or thyroid imaging, and a 10 megahertz is breast, thyroid, and superficial veins. Because remember, the higher the signal, the more superficial we are recording because it's not penetrating as much. Say we're going to do musculoskeletal imaging, we'd actually use 15 megahertz because these are structures that are very close to the skin. An ultrasound probe, also known as a transducer, is a device that converts the pulse of electrical energy generated from the equipment to mechanical energy. For example, high energy frequency sound waves that travel through the tested material. The probe holds the crystals that send and receive the sonic pulses. The sound waves, after bouncing back from the test subject, are captured and converted by the probes into an electrical energy pulse. When we're choosing a transducer, we have to think about what frequency we're using and what type of resolution that we are going to get. A 12 megahertz transducer has very good resolution, but can't penetrate very deep into the body, whereas a 3 megahertz transducer can penetrate deep into the body, but the resolution is not as good as the 12 megahertz. So the frequency also affects the quality of the image. The higher the frequency, the better the resolution. The lower the frequency, the less the resolution. An energy ultrasound probe, also known as a transducer, is a device that converts the pulse of electrical energy generated from the equipment to mechanical energy, or high-frequency sound waves that travel through the body. In a moment, we're going to take a closer look at the construction of the ultrasound probe, but we're going to look now at the transducer construction. The transducer is the area in the probe that actually sends out the signal and receives the signal, and is made up of small crystals. Notice the crystals here when compared to a single human hair. The transducer is made up of crystals, and these crystals are electrical, mechanical types of energy devices. When they get compressed and then the compression is released, a sound is released. If they have no signal, there's no sound created. If you're pulsing it, the signal is turned on and off. During that period of time of flexion, the crystal actually sends out echoes. If the crystal is not sending out an echo, it is receiving echoes. And that means that 99% of the time, there is no signal created, and 1% of the time, there is a signal created to create echoes. There are two different modes for the Doppler: pulsed wave and continuous wave. With a pulse wave, we're sending signals and then waiting for the signal to return to analyze. With a continuous wave Doppler, we're using two sets of crystals. One basically is sending and one is receiving, and they're doing this simultaneously. Here we see the flexion of the piezoelectric crystals that create the echo or signal. Let's take a look at the internal components of an ultrasound probe. Here we have a convex type of probe demonstrated. There are many types of probes and different frequencies that they utilize. But you'll see that we have a backing material, and then inside the probe we also have the piezoelectric element, which is known as the transducer. This is coupled to the acoustic lens and the matching layer. The piezoelectric element is the crystal size that both sends and receives echoes. And you'll notice how small the crystals are, because here we have a comparison for a piece of hair. When we look at the lens itself, the acoustic lens produces a mechanical focus of the ultrasound beam and serves as a matching layer to couple the probe to the patient. The matching layers lie between the acoustic array and the lens and commonly consist of several different types of material. The thickness is generally a quarter of the wavelength of the array's center frequency. The purpose is to maximize transmission of energy from the acoustic array to tissue by reducing reflection and increasing the amount of frequencies emitted by the probe. An image is formed on the LCD monitor from an array of pixels or picture elements that are arranged on a matrix or screen. They create the image that corresponds to the intensities collected and digitized. The brightness of the dots or the pixels is proportional to the strength of the returning echoes. The returning echoes are recorded as data which is corresponding to the intensity of the echo. We utilize this data and change the numbers into intensities. So we previously changed analog to digital or continuous to data. And now to be able to visualize this with our eyes, we're going to have to change it back to analog. So we take the numbers and reverse the process and demonstrate the shades of gray instead of numbers on the screen of our monitor. The sonographer needs to not only understand how the equipment works, but they also need to have the hand-eye coordination and the ability to change the different settings dynamically so that when they have the probe oriented to the patient, it is oriented to the correct position to demonstrate the anatomy. How do we create an image on the ultrasound monitor, or how is an image formed? The amplitude of each reflected wave is represented by a dot or pixel. The position of the dot or pixel represents the depth from which the echo is received. The brightness of the dot represents the strength of the returning echo. Combining all these factors, we can create an image. Common scanning planes include the sagittal plane, and this plane runs along the longitudinal axis of the body. The coronal plane, and it runs across or perpendicular to the sagittal plane. And the transverse plane, also known as the axial plane. It cuts horizontally across the body, providing a view from top to bottom. Ultrasound generates two-dimensional images of three-dimensional structures. Understanding the relationship between the patient, transducer, and the anatomy is crucial in taking orientation and looking at the ultrasound screen. Here we can take a look at the longitudinal plane. Notice that the sagittal indicator is toward the patient's head. Here we can see that the transducer has been turned so that the indicator is towards the patient's right, and this will produce a transverse plane. Let's take a moment to explore how ultrasound creates color Doppler. The machine superimposes color on the traditional B-mode brightness mode image. Blood flow and direction are represented by the colors. The Doppler effect is used to evaluate and quantify blood flow. The transducer is the sound source and receiver. Flow is in the motion relative to the transducer. Doppler produces an audible signal as well as graphical representation of the flow. Using the Doppler effect, we can look at the velocity of the flow. So we look at the amplitude of the waveform. Notice that the amplitude of the waveform is higher and the waveforms are closer together with a faster flow. As the flow slows down, there is a difference of waveform. Notice now that the waves are a little bit wider and much lower in amplitude. This is how we create the information to be able to show the blood flow within the body. There are two types of Doppler. One is continuous wave and the other is pulse wave. Continuous wave uses different crystals to send and receive the signal. One crystal constantly sends a sound wave of a single frequency, and the other constantly receives the reflected signals. The advantages of continuous wave Doppler is that it can accurately display flow of any velocity without distortion. The disadvantage is that it samples everything along the Doppler line, and you cannot position the Doppler to listen at a specific area along the path. The pulsed wave Doppler produces short bursts or pulses of sound. It uses the same crystals to send and receive the signal. This allows the same pulse echo technique that is used in 2D image formation. The advantages of a pulse wave Doppler is that it can sample at a specific site along the Doppler line. The location of the sample is represented by the sample volume. The disadvantages of the pulsed wave is the maximum velocity which can be displayed is limited. The signal will always distort at a given point based on the transducer frequency. Continuous wave Doppler is widely used in cardiology applications, and it requires the ability to display very high velocities without aliasing or distortion. While the pulsed wave is used in all other clinical applications. What is power motion imaging? It's a Doppler technique that looks at high amplitude, low velocity signals. It's similar to color Doppler, but it doesn't indicate the flow direction. Instead, it focuses on detecting blood flow intensity. In PMI, or power motion imaging, we are looking for high amplitude, low velocity signals. Broadband ultrasound involves ultrasound probes and transducers that operate across a wide range of frequencies, allowing for detailed and precise imaging of various tissues and organs within the body. It combines anatomical images with information about movement, velocity, softness, and other physical characteristics. Broadband flow technology yields smaller sample points processed simultaneously, providing a more detailed profile of the hemodynamic subtleties. Let's take a look at attenuation and gain. Sound is attenuated by the tissue, the density and the thickness of the tissue that the sound is propagating through. Attenuation is defined as the deeper the wave travels in the body, the weaker it becomes. This incorporates the principles of reflection, absorption, and refraction. The more tissue there is, and the thicker the tissue or different densities of tissue, the more attenuation of the signal. To compensate for signal loss, we need to adjust the gain based on the depth of the signal or based on the echo that we're receiving. Gain controls receiver gain only and does not change the power output. If we increase the gain, the image becomes brighter. If we decrease the gain, the image becomes darker. All ultrasounds have gain control. It's often a knob, button, and/or a series of sliders on the console, and it's one of the most used and adjusted scanning parameters. Gain is a uniform amplification of the ultrasonic signal that is returning to the transducer after it travels through the tissue. So rather than brightening the monitor, the image on the screen is whitened by a uniform margin, as though the returning signal is stronger than it is. This makes it easier to see. We looked at strong echoes. Now we're going to look at weaker reflections or the gray echoes, which we normally see throughout the entire image of the ultrasound. Different variances of shades of gray. That's what makes up the image. If we don't get any reflected echoes at all, they're totally absorbed, this is going to give us black dots or pixels. And this is found in fluid within a cyst, urine, and blood. It's called echo-free. And here we see images that have totally areas of echo-free or black that define the different areas of fluid within the body. Let's do a basic overview of the types of transducers. If we're going from 4 to 13 megahertz, we have what's called a linear transducer or vascular probe. Linear transducers are used for musculoskeletal imaging and looking at certain vessels like carotids, and ultrasound procedures for line placing or nerve block in regional anesthesia. Thyroid ultrasound is also done with this kind of transducer, since the thyroid lies directly beneath the skin. With this type of transducer, we're getting the areas closer to the skin. We're not seeing the deep reflections from inside the abdomen. Convex or sequential arrays also are known as curved or curvilinear arrays. They're very similar to the linear array, but the crystal elements, the piezoelectric crystal elements, are arranged along a curved transducer head. Ultrasound beams are emitted at 90 degrees to the transducer head. This arrangement results in a trapezoid field of view due to the divergence of the ultrasound beam with increasing distance. This allows for a wider field of view, but with decreased line density and reduced lateral resolution. Now let's look at a phased array probe. The phased array ultrasound probe is typically 2 to 3 centimeters long and consists of 64 to 128 elements. It is smaller assembly than a sequential array and can be either linear or curvilinear. A sector field of the view is produced by all elements firing to create a single waveform. Small delays in element firing allow for electronic field steering and focusing without moving the ultrasound probe. All the elements will be fired multiple times with different degrees of steering to create an image. Ultrasound knowlwdge is a term that describes the manipulation of ultrasound knobs and system controls in order to obtain the best possible image. Knowlwdge involves the adjustment of various settings such as power, probe, presets, depth, gain, and time from the original setting. We're making a compensation. Knowlwdge is an essential skill for ultrasound users as it can improve quality and avoid misdiagnosis. To the left, we can see the difference between high and low gain, the difference in the amount of information we're able to see. Gain is the strength of the returning echoes, and novices tend to overgain the image. But gain can be adjusted from the top to the bottom or all at once to enhance the image. Ultrasound waves are attenuated by the body, and the deeper they go, the weaker they become. We can actually adjust how deep these waves enter the body by using the depth control on our ultrasound machine. Ultrasound frequencies in diagnostic radiology range from 2 megahertz to approximately 15 megahertz. Higher ultrasound frequencies have shorter wavelengths and provide better detail and spatial resolution. However, shorter wavelengths are more easily absorbed and attenuated. Therefore, higher frequencies are not as penetrating, and this explains why frequencies are used or different frequencies are used for different areas of the body. Medical ultrasound probes or transducers contain more than one operating frequency. If we take a look at this list, we can see how the frequencies are used typically in an ultrasound examination for the different types of tissues or regions of interest that we want to display. M-mode uses a phased array ultrasound transducer, which is typically 2 to 3 centimeters in length and consists of 64 or 128 elements. It is a smaller assembly that a sequential array can be either linear or curvilinear. A sector field of view is produced by all elements firing to create a single waveform. Small delays in the element firing allow for electronic field steering and focusing without moving the ultrasound probe. Color flow Doppler is used frequently in sonography to semi-quantitate overall blood flow to a region of interest. Depiction of the general velocity and direction of flow within the heart and blood vessels is of primary importance in echocardiology and vascular ultrasound, respectively. Pulsed wave Doppler relies on the Doppler effect, which states that moving objects alter the characteristics of sound waves. It sends short pulses of ultrasound and then analyzes the reflected sound waves between these pulses. The same piezoelectric crystals are used to both send and analyze sound waves. These crystals rapidly alternate between these functions. This is used to be able to show us a range of information, and it is selectable by the user. The limitations in pulse wave Doppler are on the maximum velocity and accuracy of recording the pulse waves. We'll end this presentation by doing a step-by-step guide on how to choose settings before performing an ultrasound. First, turn the machine on. Next, select the correct probe. Then optimize your image quality. Explore different modes. And remember that practice and experience play a significant role in mastering ultrasound settings.